Daggers all front on equal, it's like only true two. Well, get them to slip and then we'll take a sip of the rare old man.
So happy Tuesday, everyone. This is a copy of today's notes. This is an attendance register. Does anyone have any questions before we get started? Today, I can tell you that today's topic is very exciting, and it's going to be very new for you. This is going to be unlike anything you've ever seen before. Not only is it going to be unlike anything you've ever seen before, but it's going to be unlike anything you're ever going to see. So it's really a once-in-a-lifetime kind of lecture. You'll never see this previously, and you'll never see it in the future either. Well, from somebody else necessarily. It's a very special topic. And that's true about this lecture and the next one and a few more. So if anybody can remember, last time we talked about objects. We talked about information hiding, objects, and how to identify objects. So today we're going to talk about something called responsibilities. Now objects, just as a little bit of context, objects correspond to nouns in the requirement specification. Responsibilities correspond roughly to verbs. So there's a mapping from natural language to software design. And in some ways, that's what we're doing. We're trying to figure out, given a natural language set, text written in English or maybe Chinese. We're not going to cover Chinese. How to take the natural language set and transform it into a software design. So we take a natural language specification and transform it into a software engineering specification. That's really what this is about. It's really special. Maybe I can open the window again until the next jackhammer comes. So there are two kinds of responsibilities that an object maintains, right? Knowledge or data is one kind of responsibility, and the actions that an object can perform on that data. So the methods. So data and methods. That's what an object is, right? A collection of data and methods. And it represents the purpose of an object in a system, right? The why and the what of an object. Not the how, remember. So the why and the what. Responsibilities define the services provided by an object to the rest of the world or the system or all other objects. Right? Information that the object can return to a client object, or an action the object can perform for a client object. And it represents, responsibilities represent only the public actions or the public services. Generally speaking though, these public services are public methods. So you've seen public methods in Java, right, already, and private methods in Java. So responsibilities generally correspond in Java to public methods. And they generally don't correspond to the data, let's say, because data is always encapsulated in an object. So you never have direct access to data in an object. Data members of objects are always private by default, right? So there may be other data and other knowledge and actions that need to be implemented to carry out some responsibilities, but those are hidden, right? And again, we talked about this last time, and we're going to repeat it again. And this is not the last time we're going to repeat this. We focus on what a class does, not how it does it, right? So we're all, as computer scientists, obsessed about how things are going to get done. That's a reasonable question, but we're not going to talk about that. We're not going to discuss that during the design phase. The design phase is all about what classes do, not how they do it. Does anybody remember one of the reasons that is the case? I mentioned this last time. It might be difficult for you to remember.
The inheritance.
The reason we concentrate on what a class does and not how is because there are an infinite number of hows. Right? How something can get done, there are an infinite number of solutions to how something can get done. So the person that decides how something that's going to get done is the person that actually implements the class. So everybody's assigned classes in your coursework, and you distribute the classes that you define amongst your team. And then if you get a class and it's assigned to you, you decide how it's going to work. Not everybody. You can talk to other people, but that decision is up to the person who gets the object or has to implement the object or the responsibilities. And like I said, there's an infinite number of hows. So your discussion, if you decide, oh, let's talk about how, you have to be aware that that discussion has no ending to it. You can talk about how for 1,000,000 years, right? There's no end to that discussion. However, if you have a discussion about what classes do, then your discussion will be much more constructive. So identifying responsibilities, put a star on this slide in your notes because this is a very important slide. And it corresponds to a slide from last week, which was identifying objects. There was a slide called Identifying Objects. So how do we identify responsibilities? In other words, how do we extract them from the natural language text specification? We examine verbs in the requirements specification. So each active voice verb may indicate a responsibility. Turn passive voice sentences into active voice sentences and examine. Examine information nouns in the requirements specification. So numbers, for example, anything that describes a quantity. Information nouns may become an attribute of a class or part of a composite class. So we're going to talk about those in the forthcoming lectures. Information words, look out for words like how much, how many, how big, and those sorts of things. Sizes and amounts and quantities. And then perform a so-called system walkthrough. A system walkthrough is when you actually imagine a piece of software working. So you press the start button. What does the first screen look like when you press the start button? What are the options given to the user? Right? Maybe you have an option that says Run Program. There's a button that says Run. So you click on that button. What is the next window that appears? What does it look like? You can draw it out. You can draw it out using tools, or you can draw it out with your hands. That's a system walkthrough. Postulate a variety of scenarios and execute the system. That's why the execute is in quotes. There is no execution. You're just showing how, not how, but what the system looks like. Look for places where something happens based on the system input, right? Has each action been noted? Have the responsibilities for each action been identified? And this is what we're going to talk about today, by the way. So this is not the end of the story. So from the last lecture, we learned how to extract classes and objects from a natural language specification or a requirement specification. We look at those classes again, the candidate classes, and we make a note of the following, that every class has at least one responsibility. The name of classes may also imply responsibilities, and the statement of purpose may imply responsibilities. So we may derive new responsibilities based on experience and the names of classes. And that attributes of the class may need to be managed or will need to be managed, right? All those information nouns that we just talked about. Now, this might sound very abstract to you at this point. And it is abstract on some levels. It is trying to raise the level of abstraction that didn't exist before. Now, if you were thinking, oh, I would like to see concrete examples of this in action, where would you look? Anybody have any guesses? Where would you see this concrete examples of these concepts in action? Where's the attendance register? You pass that forward. Anybody have any guesses? It's the same question I asked 1 week ago. Does anybody? I guess it's hard to remember 1 week ago. So I asked a question a week ago. Where would you find examples of objects in your day-to-day experience? Does anybody remember that question? I guess a week ago was too long ago. In the Java library. So you can find examples of these in the Java library. So every method you see in Java is an example of a responsibility. Every object and class you see in Java is the example of an object or class. Right? So you have thousands and thousands of examples, right, that you're using already in your Java class. Right? So you're seeing the implementation of all these concepts in the Java library. So there's a very concrete source of examples of what we're talking about here. So assigning responsibilities. So we've gone through the responsibility extraction process. We have a list of candidate responsibilities, and this will be a class, and this will be a class exercise, actually. Once we've done that, we're going to have to assign those responsibilities to classes, right? Because that's what classes are, a collection of related data and the methods that operate on the data. Examine the context in which the responsibility was identified, and use the requirements specification as well as class definitions. Some assignments will be obvious, others will require some thought. So usually a responsibility or a verb is mentioned in the context of a noun, a subject noun or an object noun. And usually they go together. They make lots of progress during this class. So we want some guidelines on distributing the responsibilities. We want to have even distribution of intelligence. So when we add a responsibility to a class, that class increases its intelligence. But we don't want one class to have all of the intelligence. We want to distribute it evenly. And again, if you look in the Java library, you'll see that the intelligence is distributed evenly. Each object has, for example, 5 to 15 methods, right, that are distributed evenly. We state responsibilities as generally as possible to start off with. We keep the data and the methods that operate on the data together. We keep information about one thing in one place, as opposed to keeping information about one thing in multiple places. Anybody know the reason for that rule? Can anybody imagine the reason for having such a rule like that? Keeping information about one thing in one place. Christopher Smith. Can you imagine why this could be a guideline? Keep information about one thing in one place, as opposed to multiple places.
They don't lose information you need to use. They don't lose information.
So you don't lose information? That might be an argument for the contrary, actually. Any ideas? Can anybody help Chris out on this? Has anybody tried to keep information about one thing in multiple places before?
If you have to modify it or maintain it, you might have unintended side effects.
That's right. It's because if you try to maintain information about one thing in multiple places, it becomes inconsistent, right? You may update the information in one place, and then it's different from the other place, and then you have a conflict. Right, so if you want to get the time, you keep the information about the time in only one object called time. Because if you had multiple objects called time, it would be hard to synchronize them, or you get inconsistent information. And then sometimes responsibilities are shared amongst multiple objects. So we talked about this distribute system intelligence evenly. So this is a little bit more on that theme. System intelligence. So you can think of a method or data as intelligence, right? So system intelligence represents what the system knows, the actions the system can perform, and the impact the system has on other systems, right? Class intelligence is determined by two major components. What's the service? What services does it provide? That means that can be thought of as what methods, what public methods does the class or object have? And what methods does it use? In other words, what methods does it have in order to fulfill its responsibilities via other objects outside of itself? That's called class intelligence. So if I am an object in, for example, it's not a very exciting example, but if I'm an object called time and somebody needs the time, they ask me, right, get time. Time object, get time. And when that happens, I am the server. As a time object, I am the server. Now, if I am a time object and somebody asks me for the date, I might outsource that to another object called date, maybe. So if somebody says time, get date, I might just take that responsibility and pass it on to the date object. In that case, the time object turns into a client, right? So that's what these server and client terms are meaning. And I think those are terms that you're all familiar with, right? If you're requesting information from something or somebody or somewhere, you're the client. If you're giving the information, you're the server. I think you all are familiar with those terms. A client view of intelligence is how many other classes does this class know about? So every class knows about some other classes, and how many is the question. And the greater the number, the greater the intelligence of that class. And how much does it need to know about other server classes? So some examples are collector objects or collection objects. So you're all familiar with arrays and sets. Collection objects have low intelligence. They have the same or the little effect on the objects that they store, right? So if a list or an array might just store some numbers, and the array might not have any effect on those numbers that are stored in it. The example that we keep coming back to, this drawing editor, piece of software to draw figures in, and like rectangles and squares and circles, has high intelligence. So it knows about a lot of other classes. It needs to coordinate lots of other classes. And one from the CIA, Central Intelligence Agency, without the agency. Centralized Intelligence. So this is something that you probably experience now in some ways, where you're writing software and you're putting all of your methods and data in one object. Right? That's sort of the stage that you go through in the beginning, right? So all of you are doing courseworks in Java, and currently all of your methods and data are in one object, right? Has anybody written a program with more than one object yet? Not yet. You have. Okay. How many objects did you use so far?
Only 3.
3. Good. That's great. That's great. That's a big step. So as soon as you create another object, you're distributing the intelligence. So taken to an extreme, one object incorporates all of the system intelligence, right? That's called centralized control. You can think of that as a top-down design with the main program under complete control and all other objects serving as simple data structures or entities. Are there advantages to that idea? Yes, there are advantages. If your whole program is in one object or one class, it's easy to follow the execution, the flow of execution. It's easier to get an initial understanding of the overall control of flow and the information flow, right? It's linear from top to bottom. It's easy to follow the program. But it does have its disadvantages. It does have disadvantages, right? It hardwires the system behavior and makes it less adaptable, right? And you integrate multiple design decisions into a single class, and it makes it less likely that changes in this class don't affect the rest of the system by accident, right? So any changes at the top have these unexpected consequences at the bottom. And there's less code sharing and less design sharing. So you won't see any examples of centralized intelligence in the Java library. Another extreme example that you'll find when you go into industry, you're not there yet, but if you decide you want to be a software developer in industry, you will find examples of centralized intelligence. And sometimes what can happen is somebody will write a method, they'll check it into the repository, somebody will check it out, expand the method, check it back in, check it out again, expand the method, and after a while, the method is very, very long. Right? Maybe it's 1,000 lines long, maybe it's 2,000 lines long, maybe it's even longer, like thousands of lines long. When that happens, at some point, nobody is willing to modify the method anymore because they're afraid they will break it. It's like a stack of cards that's got too big. Nobody's willing to adjust or add any more cards because they're afraid if they touch it, the whole thing will crumble. That's a consequence of centralized intelligence, and that is something you will experience when you get to industry. There's also a euphemism for this, for that phenomenon. It's so common, there's a euphemism for it. Remember, everybody, remember the euphemism for failing projects? Does anybody remember that? Pull up. There's a euphemism for software that has suffered the consequences of centralized intelligence and can no longer be modified by anybody. There's a term for this, and I bet you've heard the term before. You will definitely hear it in your future if you stay in this business. It's called legacy code. Has anybody ever heard that term before? That's legacy code. Legacy code is old and delicate, and it's usually a method that's gotten so long and so complicated that nobody is willing to touch it anymore, right? And it becomes like fossilized. So nobody's willing to touch it because they're afraid it's going to break, and nobody's willing to delete it either because they're afraid something else will break, right? And so it just becomes this thing, this permanent fossil. It becomes a legacy. It turns into legacy code. And probably the majority of code, in the world is legacy code. It's because they didn't take this module. They don't know about distributed intelligence. Whoever writes those methods never went through this great material. So if you look at the Java library, you don't find centralized intelligence, you find distributed intelligence. So the goal in this module, and for the rest of your life, by the way, is to distribute intelligence as evenly as possible amongst classes. So we minimize the number of intelligent classes, or how do you know when a class has gotten too intelligent? And you will experience this in your degree. Is you're working on a class or an object, and you find out it has too many methods. Like, you get to a certain point where maybe your object has 20 or more methods, and it's too complicated. It gets very difficult to manage. Maybe you're spending all of your time scrolling up and down, right? It becomes very difficult. Then you know there's an alarm that goes off that says, oh, this needs to be divided and conquered. So minimize the number of. In the ideal world, all classes are of equal intelligence, and every object doesn't know very much. Every object encapsulates only a few related design and implementation decisions. So when we want to check that, if we're doing a good job, we compare the number of responsibilities assigned to each class, right? So the number of methods and data attributes. If it becomes too big, then we need to do something about it, right? So if a class has too many responsibilities, maybe the responsibilities are expressed in too low level of a detail. Maybe some have to be moved to another class, and maybe the class needs to be subdivided. Right? That's especially important when you're actually working on a piece of software. So for responsibilities, we state the responsibilities as general as possible. So an example of Imagine we have our drawing editor program, and there's an object called line element. So a line element knows how to draw a line, and a rectangle element knows how to draw a rectangle. So we say that both know how to draw themselves. So in other words, we might have a method called draw. Right? Line element draw, and rectangle element draw. There's no point in having a line element object and then a method called draw line element inside that object. Right? That's not very good design. So if we follow this guideline, it leads to more shared responsibility, it leads to more general classes, and it leads to more code reuse, right, as opposed to not being able to reuse code. And we keep related behavior with related information. In other words, related methods with the methods that operate on the data are in the same class as the data, generally speaking. If an object maintains particular information, it should be responsible for performing any operations on that data and vice versa. And the exciting example I use a lot is the time object. And this is what we talked about a little bit already, keeping information about one thing in one place. So maintenance of specific information should not be shared, right? This leads to duplicate information, which may lead to inconsistency. Right? If we try to maintain the same information in multiple places, it inevitably becomes inconsistent. There might be a rare situation that more than one object must know about the same information, right? So we assign the information to one object or one class, and it has very few other responsibilities. Like time has only get time as a responsibility, right? And that's it. If all the objects requiring information have little else to do, they might be collapsed into a single object or class. And we create an object that takes on the responsibility of managing that information. If the information is very special, we just create an object whose job it is to maintain that special information. Right? A typical class, another typical example, for example, in the drawing editor might be user, a class called user, right, that stores usernames and passwords. A username and password. One of the last guidelines is to split shared responsibilities. So sometimes responsibilities need to be shared amongst several classes, and they're called compound responsibilities. For example, displaying a drawing, right? If we have a complicated drawing with lots of circles and rectangles and edges, maybe we have colors, textures, that responsibility will have to be shared amongst several objects, right? And we're going to see how to do that, by the way. We're going to see how to split objects up into that get distributed. Any questions so far? I think it might be time for an in-class exercise. So this is the first in-class exercise. So this is to be done in pairs right now. Yeah. So it's called identifying objects. Exercise 1, identifying objects. You write down your name on that piece of paper and the name of your team partner. So you give this back in pairs of 2. So, yeah, well, you can take one per person, but when you give it to me, you give me one that's for 2 people, a pair of people. So, given the partial specification below, identify a list of candidate objects. This exercise is to be done in groups. Actually, it's done in pairs now. At some point, Tom is going to put you in groups. Next month, Tom is going to put you in groups in December. The specification is adapted from Worsbrock et al. Please follow the guidelines given in lecture. So what are the guidelines for classes identifying objects or objects? Which, is that the class exercise? Okay, I guess I didn't print enough for every individual, so you really have to pair up. You have to pair up and do them in teams of 2. So I only printed, I think, 12 or 13.
I'm sorry, I'm not quite sure how many people in the one group. 7 or?
There are 2 people for this exercise, so you pair up with one other person and do the exercise. Yeah. You guys have 2. Is it okay if you share one? Any other pairs of people that need one? Is it okay if I? Extra one? I guess you 3 can form a group of 3, or you only have one bunch. Okay, if you are a group of 3, then we have an extra. So in order to do this exercise, you have to remember how to identify objects, right? So you have to be able to go back and look at this slide. Guidelines for identifying objects. Basically, this exercise tests to see if you can understand what's given here, these guidelines. So the partial specification is given here, and it's only a few paragraphs. It's not a complete specification, it's a partial specification from the drawing editor. And from that partial specification, you identify a list of candidate objects. Right? Does everybody understand what they're expected to do? Anybody need more clarification? You're all surprised, shocked and surprised by this exercise. If you have any questions about this, feel free to ask any time. Like you might be wondering what to do, or if you're doing it correctly, then you can just ask. Also, I have extra copies of. Do I have extra copies? I have some extra copies of the previous lecture. If anybody was missing last time. Anybody else need a copy of the previous one? This is a good exercise, by the way. This is really good. It's not very difficult, but it's really, really good.
Are there definitive number of objects in it? Is there a correct answer?
Say it again.
Is there a correct answer? Is there a definitive number of objects in it?
Is there a correct answer? That is a good question. What's your name? Stefan? That's a good question. There is more than one correct answer. So that's one of the beautiful things about software design. There are multiple correct designs. There are infinite number of incorrect designs. But there are multiple correct designs and correct answers.
Well, I think these classes should be created and then some classes should be lined
Yeah, I think
consider
you can use them to create
I think if you split the outcome superclass, make the superclass one create.
Does it make sense?
There also subclasses of lines, rectangles,
Yeah.
and there is another superclass. Edit the existing.
It's not that complicated.
Okay, just
So you're just looking at the text, and then you're looking at the first rule. A class or object corresponds to a noun. So you're looking at this text, and then the first step is to identify the nouns. Yeah. For this one, the only thing that you need to concentrate on are the nouns. The nouns. So classes and objects correspond to nouns. So this exercise is identifying objects. Classes. That's all. That's it.
now.
Yeah.
Yes, creating one
That's
is
part of
reserved.
that's step one. Yes.
This object.
These are steps of step one is here to identify the nouns. Step one. So you have to know what a noun is. I guess it's more difficult if you're Chinese. Do you study nouns in Chinese? Like, do you have nouns? Do you have verbs? So you find out the nouns, then there are some nouns that are not singular, so you change them to singular. That's step 2. When you guys are studying in Chinese, what do you call a noun? What is the definition of a noun?
It's easier. Make it just easier.
Okay.
Drawing elements.
Okay. Okay. So when I was in school, we were taught that a noun is a person, place, or thing. What's the definition of a noun? Excuse me? Tools. Tool. So a tool is like your pen is a tool, right? It's a device that lets you accomplish something or it gives you a special skill. Like a screwdriver is a tool, right?
So we should have 2 functions like this.
So tool is actually a noun. Yeah, right? A tool is a noun. So the first step is actually to look for the nouns. And tool is a noun, right? So tool is a candidate object. Actually.
Yes, but it's not something physical already. And create when it's creates you are about to create something, it's empty. So they all this is not included.
We can't decide
to create like
Yes, but if you
Cross-check the guidelines.
to edit, it's not empty. If you are about to edit something, it's not empty.
I mean like when you're creating then it'll be empty.
so
Yes, but look at the creation, sequence selection is empty.
Correct.
Look at this if I'm wrong, just
That makes sense.
so very
Okay. Okay. Question?
Let's check for the right track.
Sure.
Yeah, you're on the right track. You're on the right track, but so make sure that all of your nouns, objects are nouns. You have an object here that's not a noun.
It's function.
Actually, it's not a method either. It's an attribute. Yeah. So that means an adjective. It's an adjective, right? You put down an adjective as one of the objects. So adjectives are not objects. Nouns are objects, right? So that's a good thing to know. Let's get those bad boys back up there.
always a verb and an adjective.
So, is selected a noun? Is the word selected a noun?
It's an adjective, is it described?
It's an adjective,
Capital
yeah.
adjective.
The selected thing.
It describes the noun.
It's a descriptive term applied to a noun, yes. So selected is not a good candidate for an object. It's a good candidate for an attribute of an object. Like you can imagine having selected as a Boolean value inside an object. True or false?
So what about cursor? It is a
Is
noun.
cursor a noun?
It is a noun, yeah.
Then it's a candidate object.
Oh.
That's the first rule, the first guideline. Why is that so complicated?
Because I just assumed it would be an object. It's just like a cursor.
The rule is if it's a noun, it's a candidate object.
Candidate object. Does that mean it's not necessarily, but it's a candidate?
Correct. Correct. It's a candidate object.
Okay. You just try to work my head down.
So that's a good. The cursor is somehow very special in this application in a drawing editor, right? The cursor is special. Okay, so we're out of time. So I'm going to ask you to hand these in at the beginning of the next lecture, which is actually in 2 weeks, because we have Greganog. Tom and I are going to be in Greganog, Wales next week. So the next lecture is in 2 weeks, and you're going to pass these in. You're going to pass the exercise in. We're going to go over the solution. Happy Tuesday.